Jai Hind, dear students. I am Dr. Vimles Misra from Ajay Kumar Garg Engineering College, Department of Applied Science and Humanities. Today, we are going to discuss Unit 2. This is Electromagnetic Wave Theory, which is the course of Engineering Physics. Subject code is KS101T. So, today we are going to study electromagnetic wave equation in conducting medium and skin depth. So, let us start. So, this is introduction. In year 1984, the most popular scientist Maxwell brought together the extended laws of electromagnetism such as Gauss law, electrostatic, Ampere's law, Faraday law in the form of 4 equations known as Maxwell's equation. So, complete set of relations giving the connection between electrostatics and charges in motion like current, electricity, electric fields and magnetic fields, electromagnetism were divided theoretically and summarized in 4 equations. So, these are the topics which we are going to cover. So, first one is continuity equation for current density, displacement current modifying equation for the curl of magnetic field to satisfy continuity equation, Maxwell's equations integral differential form and their physical significance, electromagnetic wave equation in conducting medium, and finally skin depth. So, before we starting the actual lecture, first of all we'll learn some basic concepts which are involved in this subject. First one is vector differential operator. So, vector differential operator is a very common operator which is denoted by del, which is denoted by del. This is vector operator. So, here 3 components I cap, j cap, k caps. So, this is 3-dimensional vector and this is differential operator because partial differentiation with respect to x, y and z, they are involved. So, here the symbol del by del x, del by del y and del by del z are to be thought of as partial derivatives. So, that will get applied to a real valued function. Suppose we have function phi. So, if we apply this del operator, so this will be known as grad phi, gradient phi. So, this function is scalar, but this gradient phi is vector. So, how we can think that a scalar quantity can be related to a vector through this operator which is known as vector differential operator. So, gradient is what you get when you multiply del by a scalar function. So, this is not exactly multiplication, but application of operator on a function. So, sometimes we apply on a scalar, sometimes on vector. Suppose vector. So, in case of vector, there are 2 kinds of dot multiplication. One is dot product. So, when we take dot, it is known as divergence of A. So, A is vector field. So, we have 2 kinds of field. One is scalar field and another is vector field. So, if you apply this del operator on vector through dot product, so we get divergence of A. Any quantity which diverge or converge So, if this divergence is positive, because this is scalar, either it will be positive or negative. So, if it is positive, then it means this is diverging field. If this is negative, this means this is converging field. So, another quantity is curl. Curl means curl of any vector. Curl of any vector is defined as del cross A. This vector differential operator cross A. So, this again a vector. So, this vector tells rotation of A. So, whether this vector is rotational or irrotational, that can be calculated through this operator del cross A. So, note that the result of the curl is a vector field. We can say that the curl operation turns a vector field into another vector field, and divergence turns a vector field into a scalar field, and gradient turns a scalar field into vector field. So, these three are basic operations, and we have two important theorems. One is Gauss divergence theorem. It relates surface to volume, means 2 dimension to 3 dimension, surface to volume. Here we can say that it is integrated over a surface, because double integration, in case of surface we have 2 dimension, and in case of volume we have 3 dimension. So, this dV is volume element, and this A is any vector field or function. Mathematically we call it vector function, and technically we call this field. So, vector field. And similarly, the Stokes theorem relates line to surface. So, how we can think line can be related to surface or surface can related to line. So, this line, suppose this is a line. So, this line cannot be related to any surface, but if we close this line, suppose if we close this line, somehow if we close this line, if you draw a closed line, so this closed line or closed curve can be related to a unique surface S. So, if we call this surface S, so line must be closed. So, better we call it closed line. Closed line can be related to surface. So, here integral must be closed. So, we put a symbol circle over integration. And similarly, in case of surface, surface also must be closed. Surface, if surface is not closed, suppose if we think a surface which is closed, for example, a sphere, so volume is 4 by 3 pi r cube and surface area is 4 by 4 pi r square. So, this surface is related to this volume uniquely, and if we integrate any vector field over any closed surface, and the volume which is enclosed by that closed surface, if we integrate that same vector field, the integration, this integration through this taking this divergence, in here simply A dot ds, but here del dot A dv. So, both sides will be equal, that is Gauss divergence theorem. And in case of Stokes theorem, line integration and curl of same vector field and its surface integration will be same. So, this is Stokes theorem, or sometimes we call it Stokes curl theorem. So, equation of continuity, it is basically conservation of charge. So, this is equation of continuity. So, this physical significance is that if you take divergence of J, J means current density, and rho means charge density. So, divergence of current density and partial differentiation of charge density with respect to time, if we add, we get 0. So, this equation is nothing but equation of continuity which tells conservation of charge. Conservation of charge. Here J is current density and rho is volume charge density. So, this equation is known as equation of continuity. How we can derive? This is very simple. Take the definition of current. Current is nothing but rate of change of charge with respect to time. If we change current into current density J and substitute back into equation, so this J is related to dq by dt, and if Q can be expanded in terms of volume charge density rho, so finally we can get this equation of continuity. So, now displacement current. This is actually current which is discovered by Maxwell. So, this is main contribution of Maxwell. If we think this capacitor, connected to an AC circuit, so in wire this conduction current IC flows, but here a different type of current which is known as displacement current, which is not exactly current because this medium is insulating. this medium is insulator, so conductor always flow, current always flows in conductor. So how it is possible? So Maxwell explained that because this signal is AC, so here the charge sometimes positive and sometimes negative, and also its magnitude got fluctuation, so electric field changes. So electric field changes with respect to time. So Maxwell related this displacement current to changing electric field. So this is the simple derivation where this current density, or say current divided by area, which is known as current density, it is related to changing electric field, and this E can be related as displacement vector through this relation epsilon E, where E is electric field and epsilon is permittivity of medium, and D is known as displacement vector. So this is electric field and this is also electric field, but this is called as electric field and this is called as displacement vector, and this del D by del T is known as displacement current density. So this derivation was derived by Maxwell, and using this concept of displacement current, Maxwell derived 4 equations. So this is first Maxwell equation. E dot ds is equal to 1 upon epsilon naught into q. So this is nothing but Gauss law of electrostatic. If you think, suppose a charge q is enclosed and this surface closed surface S, if we integrate or calculate flux through this closed surface S, so it will be equal to enclosed charge divided by permittivity of the medium or free space. This medium, if this air or medium, that will be the permittivity. So if this medium is air, so epsilon naught. If this medium is any medium, so then it will be epsilon. So simply, if we change this Gauss law of electrostatic, so we get an equation which is known as del dot E is equal to rho upon epsilon naught. So del dot E is nothing but divergence of electric field, and rho is volume charge density, and epsilon 0 is permittivity of surrounding medium. In this case, we have taken free space. If we multiply, so we can also convert this equation in terms of displacement vector D. So del dot D is equal to rho. So these two equations, this either this, is known as first Maxwell equation in differential form. In differential form, because partial differentiation are involved in this operator del by del x, del by del y, del by del z. That is why you call it differential form of first Maxwell equation. So its physical significance is nothing but the statement of Gauss law of electrostatic. So according to first Maxwell's equation, total electric flux over a closed surface is 1 by epsilon 0 times the total charge enclosed by that closed surface. So this is integral form. Here integrations are involved, so it is known as integral form, and this is differential form of first Maxwell equation. So this del operator is nothing but vector operator I cap del by del x j del by del y plus k del y del z. So these are unit vectors. We put a cap, so I cap del by del x plus j cap del by del y plus k cap del by del z. So this is del operator or vector differential operator, and E is electric field, rho is volume charge density, or del dot D is equal to rho. So similarly, second Maxwell equation, which is nothing but Gauss law of magnetostatics. So this is the equation number 3 is Gauss law of magnetostatic. Its physical significance that monopoles does not exist, or total magnetic flux across any closed surface is always 0, or magnetic monopoles do not exist. Third Maxwell equation, it is based upon Faraday law of electromagnetic induction. Everyone knows that this Faraday law of electromagnetic induction, which is nothing but EMF induced in a closed loop. Suppose we have a magnet, so this is south pole, this is north pole, so electric fields are coming out from north pole, and if we take a closed loop, so if flux linked with this closed loop changes, that is phi b, if phi b changes with respect to time, so an EMF is induced which flows a current. So a current flows. This law is discovered by Faraday and known as Faraday law of electromagnetic induction. So this EMF induced is equal to minus d phi by dt. So phi b is magnetic flux crossing this surface S. So by applying this Stokes theorem, we can have this differential form of third Maxwell equation, which is del cross E, that is curl of E is equal to minus del B by del T, or if we change B into magnetic field intensity, which is mu is equal to B is equal to mu naught H. So B is known as magnetic flux density or magnetic induction vector, and H is known as magnetic field intensity vector. So equation 3 is known as third Maxwell equation. So this is integral and differential form. Similarly, fourth Maxwell equation, which is based on modified Ampere circuital law. So in this equation, actually Maxwell uses the concept of displacement current. So this equation 3 is known as, actually equation 4, it must be equation. So this is fourth Maxwell equation, and its physical significance is Maxwell fourth equation represents the modified form of Ampere circuital law, that the magnetic field can be obtained by conduction current as well as by changing the electric displacement over time or electric field. So, this is integral form and this is differential form. So, here we can say that this line integration of magnetic field over any closed loop is equal to J plus this. So, J is conduction current density and this is displacement current density, which is known as JD. So, now electromagnetic wave equation in conducting medium. So, wave equation is a very general concept. If we have any wave, it must be have an equation which is like this. So, everyone knows that this is general wave equation. Here y is the parameter which is oscillating and building that particular wave. Sometimes we call it wave function in case of quantum mechanics, or oscillating parameter of that wave, and this is Laplace operator, and this V is velocity of wave. So, this equation, this partial differential equation is general wave equation, but here we will derive electromagnetic. So, one wave equation for electric field, one wave equation for magnetic field. So, we derive two wave equation for conducting medium. Conducting medium is metal. Conducting medium is metal. So, these are four Maxwell's equation. So, this is equation number 1, equation number 2, equation number 3, equation number 4. These four equations are in differential form. So, differential form means only differentiation are involved, and in free space or in conducting medium, volume charge density will be 0 and this J will be sigma into E. J is current density, sigma is conductivity. So, if metal, so conductivity is very high, E is electric field. So, we use J as sigma E. So, in fourth Maxwell equation, we have used J is equal to sigma E. In first equation, we substituted this volume charge density is equal to 0. So, del dot E becomes 0, del dot H is always 0, del cross E is minus mu del H by del T, and del cross H, fourth equation is sigma E plus epsilon del E by del T, and this term is coming from displacement current. So, taking curl of equation 3. So, what we are doing, this equation 3 is minus del H by del T. So, we are taking curl of both sides. So, taking cross product with curl. So, left hand side del cross E, and right hand side del cross, and this is minus mu del H by del T. So, because this is a space operator, here we have del y del x, del y del y, del y del z, and here time, and both commutes. So, first of all we take mu as a scalar function outside, this minus outside. So, del cross del H by del T, and in second step del by del T take outside and this operator inside, because these two operator commutes. So if we apply like this on some function, suppose del cross on some function A, or if we apply like this, so both are same, because these two operator, this del operator and del by del t operator, they commutes to each other. Commute means this operator is, suppose this is operator A, this operator B, so this must be equal to operator B into operator A. So order doesn't matter, that means these two operators commutes each other. So we have substituted the value of del cross H from equation 4th. So this is sigma E and this is epsilon del E by del T. So if we differentiate by del T, so we get two terms minus mu sigma into del E by del T minus mu epsilon del 2 E by del T square. So here first differentiation and second differentiation coming from here. So finally we get left hand side as minus mu sigma del E by del T minus mu epsilon del T del 2 E by del T square. So now we solve right hand side. The right hand side we can solve by using vector triple product A cross B cross C. A cross B cross C is basically what we do, we take middle vector and dot product of rest two vectors minus this second vector of vector C and dot product of rest two vectors. So here my minus sign is coming and this vector is this vector and rest del dot A, and similarly here is basically A del dot del. Since this is operator, so it must be in left hand side of A, and this operator del dot A is known as Laplacian operator. So if we substitute this value in earlier equation, so finally we get, because this del dot E is 0, so finally we get a partial differential equation which is wave equation in conducting medium. So if we match this from general wave equation, so from this term we can get the velocity, and this term gives the idea of loss, because in metals electromagnetic waves absorbed by atoms, so very great loss occurs when we propagate electromagnetic waves through metals. So this is our electric wave equation, or wave equation for electric field in conducting medium. And similarly, so this is plain electromagnetic wave equation conducting medium in terms of electric field. Similarly, we can derive wave equation in terms of magnetic field. So this equation, if you see, so this E is replaced by H, rest other terms are same. So here mu sigma and mu epsilon. So simply E is replaced by H. So these two equations are known as electromagnetic wave equation in conducting medium. So electromagnetic means one equation is for electric field, another equation is for magnetic field. If we take solution of these two equations, so this must be of equation 9 and 10 types. In this equation, K is not real, it is complex quantity. So complex quantity we can write alpha plus I beta. Alpha is imaginary part, alpha is real part and beta is imaginary part. If we solve, then we get E0 exponential A minus beta r and this oscillatory term. So this amplitude is decaying, not constant, because this metal are lossy. So it means that increase in the distance of the amplitude of electric and magnetic field decreases exponentially. So at a certain distance, the amplitude will become 1 by E times of the maximum value, that is E0 or H0. So this distance is known as skin depth. So if denote skin depth by delta, so R is equal to delta and EA is equal to, this is the condition of skin depth. If we solve, so we get delta is equal to 1 by beta, where beta is imaginary part of propagation constant. So solving the electromagnetic wave equation, the value of alpha and beta can be calculated, and for a good conductor, alpha is equal to beta is equal to under root mu omega sigma by 2. So mu is permeability of the medium, omega is angular frequency and sigma is conductivity. So skin depth will be 1 over beta. So this is the skin depth formula. We can solve numericals based on this equation. If we are knowing these three terms, we can solve the skin depth. So this is expression for skin depth in a good conducting medium. So these are references. So I will stop here. Thank you so much. Jai Hind.